Hey there and welcome. Today we are diving deep into the very chemicals that make life possible. We're talking about biomolecules, these incredible, essential compounds that literally build and power every single living thing. Yeah, from a tiny bacterium all the way up to us. So let's jump right in. Have you ever just stopped and wondered, what are we really made of? When you get right down to it, or what's actually inside that piece of roti or that bowl of dal you're about to eat? Well, it all boils down to just a few key types of molecules. And in this explainer, we're going to break them all down to really understand the chemistry of life. So here's our game plan. We'll start with a quick introduction to the molecules of life. Then we're going to get into carbohydrates, which are basically our energy source. After that, we'll talk about proteins, the body's builders. And then we get to the really cool part, the master plan, with nucleic acids, which leads us right into the code of life itself. All right, let's meet the main characters in our story today. The three big ones, the major classes of biomolecules you find in absolutely every living thing, are carbohydrates, proteins, and nucleic acids. A simple way to think about it, you've got the fuel, the machinery, and the blueprint for all of life. First up, carbohydrates. I want you to think of these as the primary fuel for your body. They are quite literally the energy givers that power pretty much everything you do, from thinking to running. So, what exactly are they from a chemistry standpoint? Well, the technical definition is polyhydroxyaldehydes or ketones. All that really means is they're molecules with a bunch of alcohol groups attached, plus one other special group. But you know them by their other name, saccharides. That comes from the Greek word for sugar, saccharon, which is a perfect name because a lot of them taste pretty sweet. Okay, so the most basic building block of any carbohydrate is what we call a monosaccharide. Think of it like a single Lego brick. You just can't break it down into a smaller sugar unit. This is our fundamental piece. And here are two of the most famous ones. On the left, you've got glucose. That's the sugar our bodies absolutely love for immediate energy. And on the right, there's fructose, the stuff that makes fruit taste so good. Now, they're both simple sugars, but look closely. See that tiny structural difference? One's an aldehyde, the other's a ketone. That one little change has a huge impact on how our bodies process them. Now, here's where it starts to get really interesting. See, life doesn't just use single bricks, it builds entire houses. You link two of these monosaccharides together and bam, you get a disaccharide. Link a few more, say up to 10, and you've got an oligosaccharide. But when you link a massive, massive number of them together, you create a polysaccharide. And this is a perfect picture of a polysaccharide. What you're looking at is a piece of amylose, which is a key part of starch. It's really just a long, long chain of glucose units all linked up. This is exactly how plants store energy. So when you're eating foods like potatoes or rice, this is the energy source you're tapping into. Okay, so we've covered the body's fuel. Now let's talk about its builders and its workers, proteins. If carbohydrates are the energy, proteins, well, they do just about everything else. They form our muscles, our hair, our skin, and as enzymes, they are the catalyst for nearly every single chemical reaction happening in our cells. They're a huge deal. The name protein actually comes from the Greek word proteos, which means of prime importance, and that is no exaggeration. Chemically speaking, they are polymers, polyamides to be exact, and they're built from these repeating units we call alpha amino acids. So this right here is the building block for every single protein, the alpha amino acid. Just look at it. You've got a central carbon atom, and it's connected to both a basic amino group on one side and an acidic carboxylic acid group on the other. Now, there are about 20 common types of these, and they act like letters in an alphabet that spells out all the different incredible proteins in existence. Now, amino acids have this really fascinating property. When you put them in water, the acidic proton from one end of the molecule literally jumps over to the basic amino group on the other end. Wild, right? This creates what's called a Zwitter ion, a dipolar ion, and having both a positive and a negative charge is what gives amino acids their stability. It's why they're crystalline solids with high melting points, pretty important for the building blocks of life. So how do you string these letters together to make words? Well, they link up using something called a peptide bond. The carboxyl group of one amino acid reacts with the amino group of another. A little water molecule gets kicked out, and a really strong bond is formed. You just do that over and over and over again, and that's how you build a long protein chain. But just having a simple chain isn't the whole story, not even close. Protein structure is unbelievably complex, and we organize it into 4 different levels. The primary structure is just the sequence of amino acids.
the order of the letters. That sequence then starts to fold into local secondary structures. Then the entire chain folds up into a complex 3D tertiary structure. And sometimes you get multiple chains that come together to form a final huge quaternary structure.
And this picture really shows that incredible journey. You go from a simple chain to this complex, beautiful 3D shape. And that final precise shape is everything. A protein's function is completely dictated by its structure. If it doesn't fold just right, it can't do its job, and that can lead to all sorts of problems and diseases, like sickle cell anemia. It is all about the fold. All right, we've had the fuel and we've had the builders, but now we need the master plan, the instructions. Let's talk about nucleic acids. This is the instruction manual for all of life. This is where all the genetic information is stored and transferred. So nucleic acids, which you definitely know as DNA and RNA, are also polymers, and their repeating building blocks are called nucleotides. Their entire job, their whole purpose, is to carry that genetic blueprint from one generation to the very next. So what's a nucleotide actually made of? You might think it's something super complex, but it's really just 3 parts: a 5-carbon sugar, a base that contains nitrogen, and a phosphate group. That's it. The entire code of life is written with just these 3 components, repeated over and over again. Now, one of the biggest differences between DNA and RNA actually comes down to a single atom on their sugar backbone. RNA uses a sugar called ribose. DNA uses 2 deoxyribose. And that deoxy part literally just means it's missing an oxygen atom on the 2nd carbon of the sugar ring. It is an unbelievably tiny change, but it has massive, massive consequences for how stable the molecule is and what it can do. This table lays it all out perfectly. You can see the difference in the sugar we just talked about, but look at the bases too. DNA uses thymine, while RNA swaps that out for something called uracil. And of course, the overall structure is different. DNA has that super stable double helix, which is perfect for storing information, while RNA is a more flexible single strand, ready for its active role in translating that information. And all of this, every one of these pieces, culminates in the magnificent structure that holds the secret to who we are, to what every living thing is. And here it is, the iconic double helix. It's made of 2 strands that are complementary to each other, held together like a zipper by the bases in the middle. But this zipper only works one way. Adenine, or A, always pairs with thymine, T, and guanine, G, always pairs with cytosine, C. This strict pairing rule, this is the secret. This is how DNA can be copied so perfectly, preserving the code of life across generations. So let's just take a step back. We've gone from simple sugars that give us energy to the complex proteins that build our bodies, and we ended with the nucleic acids that literally write our genetic code. We've seen how a few simple atoms can assemble themselves into the most complex and incredible molecules imaginable. It really makes you wonder, doesn't it? Isn't chemistry the ultimate story of life?